Imagine waking up at like 3 a.m. Your pager is just absolutely screaming.
Oh, man. That is the absolute worst feeling in the world.
Right. So you stumble to your laptop, you're completely blary-eyed, and you're frantically digging through the logs because your entire production cloud deployment just failed.
Right in the middle of an automated pipeline, I bet.
Exactly. Right in the middle. And after, 30 minutes of pure panic, you finally find the culprit.
And it's always something incredibly small.
Yes. Someone, somewhere upstream, copy-pasted a server name from a Jira ticket, and they accidentally included a single invisible blank space just at the end of the string.
Oh, wow. A trailing space.
Just one rogue space.
Yeah.
And that triggered an API validation error, and your entire infrastructure rollout came to a grinding halt.
It is the ultimate nightmare for any infrastructure engineer, and honestly, it happens far more often than people think.
I mean, it's terrifying how fragile it can be.
It really is. When you rely strictly on static code, your infrastructure is, well, it's incredibly brittle. It basically shatters the moment it encounters the real world.
Exactly. So, welcome to the deep dive. Today we are taking you into the engine room of HashiCorp's Terraform Associate 003 exam material.
Yep. Specifically zeroing in on the official Terraform functions and those dynamic HCL features.
Right. And our mission today is to figure out how to build what we call a bulletproof module, like a smart blueprint that actively protects itself from human error.
I love that term, a smart blueprint.
Thanks. Because whether you are cramming for this certification or, you're just tired of fixing broken state files because someone didn't capitalize an input correctly, this deep dive is going to transform how you write infrastructure as code.
And that transition, it's critical for you as a practitioner. I mean, passing the exam isn't just about memorizing a dictionary of functions.
No, nobody wants to just memorize flashcards.
Exactly. It's about understanding the underlying mechanics. How do these functions, conditionals, and loops actually interact during the Terraform plan and apply phases?
Because if you don't know how to manipulate data dynamically, you aren't really engineering infrastructure.
Right. You are just typing out very expensive manual instructions.
Yeah. And nobody wants to be a human typewriter for cloud APIs.
Okay.
So to build this bulletproof module, we have to start by manipulating our raw materials, right? Strings and collection.
The foundational building blocks, yeah.
And I don't want to just list off what these functions do, because, anyone taking this exam knows what a lowercase letter is.
You would hope so, yeah.
I want to talk about the why. For instance, the lower function. This isn't just about AWS rejecting an uppercase S3 bucket name, right? It's about the state file.
That is a brilliant distinction. Yes, the API rejection is the immediate failure, sure. But the more insidious issue is the perpetual diff.
The perpetual diff. Walk us through that.
So let's say an API doesn't strictly reject an uppercase letter, but the cloud provider's backend, it automatically converts it to lowercase upon creation.
Oh, I see where this is going.
Right. So if your hard-coded Terraform code says my bucket with capital letters, but the actual resource in AWS is my bucket in all lowercase, Terraform's state file will constantly detect a difference.
So every single time you run Terraform plan, it's going to say, hey, I need to change this resource from lowercase back to uppercase.
Exactly, even though no real infrastructure changes are actually necessary.
That is so annoying. It creates this massive, noisy state drift.
Precisely. By wrapping your variables in the lower function, you align your configuration with the cloud provider's reality.
You're sanitizing the input before Terraform even generates the plan.
Exactly. And the same goes for the trim space function. That solves your 3 a.m. pager duty scenario right there.
Oh, because it strips away those invisible leading or trailing spaces from the user inputs.
Silently and automatically, yes.
Okay, let's unpack this, because I have a bit of pushback here.
Sure, lay it on me.
If I'm the one writing the core code, why can't I just hard code everything flawlessly from the start?
Ah, the myth of the perfect coder.
Right. Why do I need to wrap everything in trim space or lower? I could just hit the space bar or caps lock myself and save all those function calls.
What's fascinating here is that in modern infrastructure environments, you are almost never the sole source of data.
Wait, really? Even on small teams?
Even on small teams, inputs are completely dynamic. They are being passed down from a root module that you don't control, or they're pulled from a remote state file.
Or generated by a CI/CD pipeline, I guess.
Exactly. Where some developer typed in a variable on the fly, hard coding assumes you exist in a vacuum.
Which we definitely do not.
No, we don't. Functions acknowledge that infrastructure exists in a messy, collaborative ecosystem. You use functions like replace to say, swap underscores for hyphens.
To strictly enforce the company's naming
Oh,
conventions.
right, regardless of what the user actually types.
I love that framing. The blueprint literally defends itself. So that handles standardizing individual text strings. Let's move to collections.
The big leagues.
Yeah, because we've got lists and maps of data flying at us all the time. Functions like flatten, distinct, length, and concat.
Oh, the exam loves those.
So how do these interact to solve an actual real-world engineering problem?
Well, let's walk through a real scenario. Imagine you are building a complex networking module.
Okay, I'm with you.
You query a data source to get a list of available subnets across different availability zones, but the data source returns a list of lists.
A list of lists.
Yeah, basically nested arrays of CIDR blocks. And Terraform's looping constructs, they usually demand a single flat list.
Oh, so that's where you wrap that output in flatten. It squashes the nested arrays into just one continuous list.
Exactly. But wait, it gets trickier. Because you pulled from multiple overlapping data sources, you might have duplicate IP ranges in that new flat list.
Oh, man. And if you try to provision resources based on that list with duplicates?
Terraform will try to build two identical subnets, and the cloud provider will throw a massive conflict error.
Enter the distinct function. So you pipe the flattened list through distinct, and it just strips out all the duplicate CIDR blocks.
Right. It cleans it right up. And finally, if you need to dynamically allocate a specific number of NAT gateways,
Based on the final count of those unique subnets.
exactly, you wrap the whole thing in the length function. It automatically counts the final sanitized list, ensuring you provision exactly 3 gateways for 3 subnets.
That is exactly the kind of workflow the exam loves to test. How these functions chain together.
Oh, absolutely. They love chaining.
We take a messy list of lists, we flatten it, make it distinct, and then grab the length. It's beautiful.
It's elegant, isn't it?
It really is. Now, part of standardizing this data involves strict data types. Because in older versions of Terraform, it was pretty forgiving, wasn't it?
Very forgiving, almost too forgiving.
Right, like if you put the number 5 in quotes, Terraform would implicitly coerce it into a number if the API asked for one.
Yeah, the good old days of implicit coercion. But modern HCL pushes for explicit type conversions.
With functions like toNumber, toString, and toBool.
It does, especially with the introduction of strict custom variable validation rules.
Why is that so important now?
Because if you are writing a reusable module for your enterprise and a specific attribute requires a strict Boolean true or false, you cannot rely on implicit coercion anymore.
So if a user passes in the string true, in quotes,
If you don't wrap it into bool, the module validation will just fail outright. Explicit conversions make your code completely predictable.
predictable is good. Speaking of predictable, let's talk about pulling data out of maps, because a massive chunk of the exam focuses on the lookup function.
Oh, yes. Look is foundational.
Because direct map access is just asking for trouble, right? So direct map access is like walking into a VIP club assuming your name is on the list.
Aha, I like that.
If it's not, you get thrown out by security and the whole operation crashes. Terraform just panics and fails during the plan phase.
Right, a total deployment failure.
But the lookup function is like a smart bouncer. If you are on the list, they just hand you a default general admission ticket so the night keeps going.
That is a perfect analogy. The mechanism of lookup is literally designed to prevent those compilation failures.
How does it actually work under the hood?
It takes 3 arguments: the map itself, the key you're searching for, and a fallback default value.
Okay, so give me an example of that in practice.
Sure. Say your deployment pipeline asks your module for the staging AMI, but your map only has prod and dev defined.
Uh-oh.
Right. A direct query like var.amis bracket staging causes a fatal error.
The VIP bouncer throws you out.
Exactly. But if you use lookup, you say lookup var.amis staging, ami-default, and it smoothly hands back that default AMI.
The switchboard routed you safely. I mean, the bouncer gave you the general ticket.
Exactly. You survived the missing key without a catastrophic crash.
That makes total sense. So our module is sanitized, it's tightly typed, and it's safe from missing map keys.
It's getting pretty robust.
But what if the input is perfectly valid, but just logically wrong for the environment?
What do you mean?
Like, say a developer successfully specifies they want an instance, but they ask for a massive, heavily provisioned, deeply expensive database cluster in our tiny sandbox environment.
Ah, yes. The classic budget-destroying move.
Right. How do we force the code to make an active choice and stop that?
That brings us to conditional expressions. We need the configuration to evaluate its environment and make on-the-fly decisions.
Which in HCL is basically just the ternary operator.
Almost exclusively handled by the ternary operator, yeah.
Here's where it gets really interesting. The syntax looks like a math equation mixed with a question mark.
It can look a bit intimidating at first glance.
It's condition, question mark, true underscore value, colon, false underscore value. You basically ask a question.
And if it's true, it executes the code immediately after the question mark.
Right. And if it's false, it hops over the colon and executes the final value.
Correct. The classic exam scenario for this is deploying different resource sizes.
Like checking the environment variable.
Exactly. You write var.environment equals prod question mark db.r5.xlarge colon db.tt 3.micro.
So the blueprint reads the current environment variable and dynamically changes its own provisioning instructions.
It's adapting to its surroundings.
I get that.
Yeah.
But I want to push back on this practice a little bit.
Oh, okay, let's hear it.
If I have dev, staging, QA, and prod environments, right?
Sure.
If I nest 3 or 4 ternary operators together to handle all those conditions, doesn't my code become a completely unreadable, tangled mess?
Spaghetti code, yes.
So how do we balance making the module smart with keeping it legible? Why not just write completely separate, hard-coded files for each environment to keep it clean?
If we connect this to the bigger picture, separating files is the ultimate trap.
Really? Why is that a trap?
Because it creates a phenomenon called configuration drift.
Oh, I've heard of that.
Yeah. If you maintain a dev.tf and a prod.tf, I guarantee you, within 3 months, a developer will add a critical security group rule to dev, but completely forget to replicate it in prod.
And then the deployment fails when you push to production.
Your environments just drift apart. You want one centralized source of truth.
Okay, I see that. But what about the unreadable nested ternaries? How do we fix that?
That's where you combine concepts. Instead of writing a massive nested ternary, you use a map combined with the lookup function we just discussed.
Wait, really?
Yeah, you create a map where the keys are your environments. Dev, staging, prod, and the values are the instance sizes.
Oh, I see.
Then you just use lookup to fetch the right size based on the current environment variable.
Oh, that is slick. Using maps and lookups to bypass complex ternaries.
It keeps your centralized logic incredibly clean and highly scalable.
That is advanced HCL right there.
Yeah.
All right, so our centralized, bulletproof module can sanitize inputs and make smart environment choices. Now we have to scale.
Time to multiply.
Because we need to deploy multiple resources. And I am definitely not copy-pasting a server block 50 times.
No, please do not do that. We enter the territory of loops, specifically the count and for underscore each meta arguments.
And listener, if you are studying for the exam, pay close attention here.
Very close attention, because this is where HashiCorp hides their most devious exam traps.
Let's start with count. It seems deceptively simple, right?
Very simple.
You just add count equals 3 to a resource block, and Terraform provisions 3 of them.
Yep. And you can use count.index to name them uniquely, like web server 0, web server 1.
But earlier, you mentioned that count relies on a numbered list under the hood. Let's walk through the exact mechanism of why that is a trap.
Okay. Visualize an array in your state file. Index 0 is server A, index 1 is server B, and index 2 is server C.
Got it. 0, 1, 2, A, B, C.
Now let's say server B is having hardware issues. So you decide to remove it from your Terraform configuration to destroy it. You drop the count from 3 to 2.
Logically, I just want server B gone.
Exactly. But because count relies strictly on the index position, when server B is removed, server C shifts to the left to fill the empty spot at index 1.
Oh, because the array collapsed.
Right. So Terraform runs a plan and says, wait a minute, index 1 used to be server B, now the code says it should be server C.
And index 2 is entirely gone.
Yes. So instead of just deleting server B, Terraform will often destroy server B, destroy server C, and then recreate server C in the index 1 position.
Oh, wow. That is awful.
You just triggered a massive unnecessary destruction of perfectly healthy infrastructure simply because an array shifted.
So what does this all mean? If count is basically a literal landmine just waiting to ruin my indexing and wipe out my production servers, why does it even exist?
It's a fair question.
Why wouldn't I just use for underscore each for absolutely everything?
Well, count isn't entirely useless. It just has a very specific, narrow use case.
Which is?
It is perfectly fine for entirely stateless, interchangeable resources where individual identity means absolutely nothing.
Like a cluster of identical worker nodes pulling from a queue.
Exactly. If they were completely identical and you drop the count from 5 to 4 and Terraform destroys one at random, it doesn't matter.
The system just routes around it.
Right. But the moment a resource has a unique identity, a database with specific data, a server tied to a specific elastic IP, you must never use count. You use for underscore each.
Okay, let's break down the mechanism of for underscore each then.
Yeah.
How does it avoid the shifting array problem?
Because for underscore, each abandons lists entirely.
What does it use instead?
It iterates over maps or sets. It maps resources to meaningful, unique string identifiers rather than arbitrary numerical positions.
Oh, so going back to our earlier conversion functions,
Yeah.
if I have a list of server names like bracket, quote web, quote app, quote DB bracket,
Yep.
for underscore each will actually throw an error because it doesn't accept lists. I have to use the toSet function first to convert that list into a set of unique strings.
Exactly. You are tying the concepts together perfectly. Once it's a set, for underscore each loops through it.
And inside the resource block, you use the each.key attribute to reference those names.
Yes. So Terraform builds a server intrinsically mapped to the string web, another to app, and another to DB.
So if I remove app from the set, the array doesn't shift at all.
Not one bit.
Web and DB are still firmly anchored to their string keys in the state file. Terraform just targets app, destroys it, and leaves the rest of the infrastructure completely untouched.
That is the exact mechanism. It tracks by identity, not by order.
That makes so much sense.
And the exam will heavily test your ability to look at a scenario and identify whether count or for underscore each is the safer architectural choice.
Okay, so for underscore each handles replicating entire resource blocks safely.
Yes.
But there is one final, more complex scaling tool we need to cover: dynamic blocks.
The dynamic block.
How do these differ, and what problem are they actually solving?
Well, while for underscore, each at the resource level creates multiple distinct resources, like 5 different servers. A dynamic block generates repeated nested blocks inside a single resource.
Okay, so if I'm building an AWS security group, that is one single resource,
Right.
but it might have 20 different ingress rules for different ports and CIDR blocks.
And hardcoding 20 separate ingress blocks inside that security group violates the DRY principle, right? Don't repeat yourself.
It makes the code incredibly bloated.
Exactly. Instead, you declare a dynamic, quote, ingress block.
Okay.
Inside that, you use a underscore each argument to iterate over a complex variable, like a map of your required ports.
But here's the tricky part, the mechanism that trips people up.
Yeah.
How do you map the variables inside the block?
Right, because normally for underscore each, you just use each.key or each.value.
Does that work inside a dynamic block?
No, and that is a massive exam trap.
Oh, really?
Yes. Inside a dynamic block, you define a nested content block. And inside that content block, you don't use each dot value. By default, you use the name of the dynamic block itself.
Oh, wow.
So if it's a dynamic ingress block, you map the ports using ingress.value from underscore port.
So the dynamic block creates its own localized variable scope based on its label.
Yes, exactly.
Unless, of course, you use the iterator argument to explicitly name it something else, right?
Precisely. If you set iterator equals port underscore rule, then inside the content block, you would write port underscore rule dot value dot from underscore port.
That is so powerful. It allows you to build incredibly complex nested configurations programmatically.
While keeping your actual Terraform code elegantly short and easy to read.
It's essentially loops within loops. At this point, the module is basically writing its own internal rules based on the structured data we feed it.
It's a beautiful thing.
Well, let's summarize the journey we've taken today to build this bulletproof module. We started by recognizing the sheer fragility of static code.
Absolutely.
We use string functions like lower and trim space to sanitize inputs and prevent those perpetual state diffs.
Yep.
We used collection functions like flatten and distinct to organize our data structures. We made map queries safe with the switchboard logic of lookup.
The smart bouncer.
Right, the smart bouncer. We navigated environment logic with ternary conditionals and learned how to bypass ugly nested ternaries using maps.
Avoiding the spaghetti code.
And finally, we explored the critical mechanics of loops. Understanding the dangerous index shifting of count, the identity-based safety for underscore each, and the localized scoping of dynamic nested blocks.
And returning to our initial mission passing the Terraform Associate exam is really just the baseline.
It's just the start.
Truly understanding these concepts is what elevates you from a beginner who treats Terraform like a basic configuration script to a senior infrastructure engineer who architects resilient, self-healing systems.
It fundamentally changes how you view infrastructure as code.
It does, and this raises an important question, one to really mull over as you study these features.
Okay, let's hear it.
If our infrastructure leverages conditionals to actively evaluate its environment, uses identity-based loops to intelligently scale, and employs dynamic blocks to generate its own internal nested rules based on complex data structures, at what point does our configuration file stop being a simple static blueprint and cross the line into becoming a living, breathing software application in its own right?
Oh, man. That is a brilliant thought to end on. The line between infrastructure and software application is getting very blurry.
Very blurry indeed.
Well, thank you for walking us through the deep mechanics of HCL. And thank you to you listening for joining us on this deep dive. Keep experimenting, keep building those bulletproof modules, and we will catch you on the next one.